Wait for it. All right, so build and monitor machine learning services in Kubernetes. A lot of buzzwords, right? It's like buzzword bingo, and kind of that's a bit of the feedback that I heard from everybody that I showed these slides to. So I figured I'd start with an actual project that I've done that kind of showcases why you'd need Kubernetes to do machine learning. So last year I went to the Tate Modern, and I saw this art piece by a guy named Christian Markley. And this movie is called The Clock. It's a 24-hour film, and it's comprised of cuts from popular culture movies. So the entire film spans 24 hours, and along every minute you see a cut from a movie that shows the current time. So the movie itself is an art piece, but it's also a clock. So it's put in museums, and you can watch throughout the day, walk in, walk out, and keep track of the time by watching the movie. So when I saw this art piece, I was blown away. I was like, oh my God, how did they do this? They probably used machine learning. They probably detected clocks within these movies because there's over 24,000 cuts in here, 24,000 clips. And I was like, how did this happen? Like, how is this done? And so my mind was kind of blown, and I thought, all right, I definitely need to recreate this. And yeah, it ended up being a little bit tricky, right? So they ended up, I found out later, they had $200,000 budget, and they had a team of like 60 people, and they manually tagged all of the places in films where clocks were shown, and they built up a massive spreadsheet. But being naive and dumb, I decided, oh, I could definitely do this. And so that was kind of my project over the last winter. And so kind of the question really is, there's nothing new in computation. There's nothing new in Turing machines, right? They're universal. They should be able to do everything. So why is machine learning now a thing? And the reason for that, there's a couple things all kind of coming together. And the basic ideas have been around for a while, but these kind of things that we have now are all coming together to kind of, out of nowhere, it's starting to do some pretty amazing things. So the first is dedicated hardware for inference. We'll get into it a bit later, but there's just an insane amount of computational power that is being dedicated to this. And then there's also the availability of large labeled data sets. So we have so much data. If you're posting to social media and you're adding hashtags, those sort of things provide labels and data for what might be in the images. And then along with that, there was these gains from convolutional neural networks. And so convolutional neural networks are just really a way of saying, finding shapes within images and being able to isolate things really easily. So one of the big mind blows for me was the AlphaGo Zero project. So as a kid, kind of, whenever any sort of conversation about artificial intelligence came up, the big thing was Go, right? Go has such a large search space that it would be impossible for us to ever conquer it. And there's kind of this AlphaGo Zero game where it played against itself for many hours, used a very large amount of computation, and it actually beat humans at Go. And so I think that was the very first step for me to be like, all right, something's definitely happening here. Something is very different from what I've been led to believe very early on. Along with this, they're now playing this game called Dota 2, which is a little unique in that it's multiple people collaborating together. And so this is another pretty large challenge that's another one of those mind blowns. On the lighter end of things, there's now YouTube channels dedicated to deep faking with Nicolas Cage. So replacing every character in a movie with Nicolas Cage's face. And yeah, it works kind of well, and it's just getting better, and it's extremely scary. So how does it work, right? It kind of, you hear these buzzwords and you hear these researchers. And so the very first thing you do is you build, clean, and label a data set. Then you build a model on that and train on that data set. And then to deploy and evaluate it. So very easy, right? When I was presenting this to somebody on my team, they were like, build a model? That's like, I feel like I'm drawing the owl here. It's like, you get the data set, you label it, it's cool, and then, train, and then it's, okay, I'm drawing the actual owl. I have no idea where to begin. And so I just wanted to incorporate an actual model I use for a project. So this is actually a model I used to train a neural network for a project we'll see later. And this is literally all of the code to do it. There's code I'm not showing that loads the data set that I cleaned out. But this is all I added to my neural network, and that trained and does things and actually works. And so, in that simplified thing that I showed before, we kind of saw, you just build, clean, and label a data set. How hard can it be? And your real-world data is always messy, terrible, and filled with garbage. Your models that you train tend to be brittle and opaque. Like, it's extremely difficult to debug where things are going wrong with it. And then finally, when you deploy and evaluate, how do you measure performance in the wild? And so with all that, kind of the machine learning development lifecycle is different from a traditional development lifecycle. Suddenly, the machine you're running on matters because you've got to use acceleration for your computation. So generally, that takes the form of GPUs or TPUs to train on these massive data sets. Another wild thing that was very new to me is that a driver update can speed up your code 300%. I don't know how many people had their code sped down by 20% with a driver update for a certain processor recently. But sometimes they go the opposite way. And the computational needs can be really staggering. And for me, this is kind of the sad panda moment. So there's this text model that came out of OpenAI called GPT-2. And so GPT-2 takes a prompt, right? A text prompt, and then it generates a whole story from that text prompt. And OpenAI decided it was too dangerous to release this model into the wild because it could be used to generate fake news and that sort of thing. And, online social media could be used to create sock puppet accounts and manipulate public opinion. So the cost to generate that network from scratch, though, on the cloud is $50,000. If you want to build and train that model from scratch, you're looking at $50,000 in cost for your cloud provider. And there's really one cloud provider that can do that training. And the computational costs for AlphaGo are actually around $35 million, which, if you're a young kid and you're excited about machine learning and you want to do something, that's a really terrible thing to see because it means, you can't really get started. Not too many kids have the ability to get $35 million to play. And so with that, and because of the computational needs, we're seeing more and more of the inference. So that's when you've already trained the model, and now you want to run the model, right? We're seeing more of that being pushed to the edge. So our phones are starting to have kind of processors built right into them that can accelerate and do the inference on them. And another reason for that is the bandwidth limitations, right? At the edge, at your phone, you don't want to be constantly sending each frame to the cloud and back and making that round trip. And so along with that, the data sets become an integral part of your code, right? That's what's being used to generate your model itself. So if you want to reproduce that model, you have to have the exact same data set. So gathering, cleaning, and labeling data becomes an integral part of what you do. And my personal favorite is that once you have a model, you can use that model to bootstrap better data sets. And I'll get into that a little bit later. So behind all this, ignore machine learning buzzwords, everything. Web development is changing in general. At Datadog, we do these internal checks for how things are going in the industry. We're seeing a lot more container adoption. Basically, it seems everybody, the community as a whole, is adopting Docker, containers in general, especially in larger environments. And we're seeing a lot of orchestration. And so something that was a little bit counterintuitive to me, based upon my kind of beliefs, is that we're seeing more larger organizations adopt Kubernetes than smaller organizations. And so I'd always kind of imagined that smaller organizations are much more nimble, much easier to adapt to new technology. And so with Kubernetes, we're kind of seeing a bit of the opposite. And I think that's because of how it allows you to work as a team. And so with Kubernetes, we're kind of doing this process of moving from individual servers to pushing to this theoretical sea of infinite computation. And the way that we're navigating that sea more and more is becoming Kubernetes. But with Kubernetes, there's kind of a trade-off. Kubernetes comes with extra complexity. So etcd, the default database where you store the state of Kubernetes, recommends 5 server instances to maintain durability. So right out the gate, before you even get anything set up, you're running any applications, just your database is 5 servers. It's a bit of a paradigm shift. And so there's a growing list of sub-packages. I'm sure you've seen or heard some of them. The biggest, most confusing one, for me at least, is all these networking layers that are being added on top, like Istio, Envoy. And so as you move to them, there's kind of the need to rethink everything, right? Development, testing, deploying. Everything is growing beyond a single dev machine, and so you've got to relearn how you do everything. And so, at least for me, I felt like Mr. Bean on top of the car, trying to control it with a stick in my lazy boy. So, okay, what are the abstractions that Docker holds? What are the abstractions that Kubernetes holds? How do they break my system? How do I run something locally? And so you just start putting these abstractions together, and you get more and more removed from the actual project itself. So you're further and further away from directly controlling the things that might break in your system. And so when they do break, I find for me personally, you need to know the default state of things when they break. Why does it break in the sublayers? And really, it's a complexity trade-off, right? Moving from software as a service to software as a utility. More and more of the things we build are becoming ingrained to our lives, right? And being able to call a ride at any time, you need to just be able to do that. It needs to just work. And more of the software systems that we're building collectively are being relied on people for more and more important things. So moving machine learning into Kubernetes, there's just way more pieces to deploy and manage and reason about how it could break. And so there's becoming a few Kubernetes native machine learning tools. The biggest one that kind of pops immediately out is Kubeflow. And it's a machine learning toolkit for Kubernetes from Google. TensorRT interface inference server. So that's like serverless for your trained models. You can just send images directly to it, get back a JSON of what's in the image. Pretty interesting. And then things like Pachyderm, which allow you to version control your data set that you're using to trade on. And if you look at the actual components, it seems like it's just a toolkit of things coalescing around. And there's a very long list of things that all consider and try to provide tools for what you might want to do. But again, way too many moving pieces. And it's intimidating. How do you get started? How do you actually start working with something so you can wrap your head around how you can get anything done? And I like to simplify first. I recommend running Kubernetes locally with GPU acceleration. And my favorite part of that is an excuse to build a really sweet gaming machine, which is technically, your deep learning machine. And this, by the way, is by this great artist, Sterling Crispin. This is his actual PC build that he works on. And it's really pretty straightforward. You download Ubuntu, set up your drivers, and snap install micro Kubernetes enable GPU, and then you can start, actually that's misspelled down there. It's a kubectl apply -f, but yeah. And then the really great thing is, in the earlier stages, all of the machine learning stuff was happening very quickly, and building these libraries could take hours. I know because I've built these libraries and taken hours out of my day to figure out the right dependency graph for which source control to build which version of which image. And so now NVIDIA has this container registry. So you set up and you install your driver, and then you're able to directly mount that GPU and see it through Docker. And so now you can just do Docker pull and get pre-built images. So this is a huge time save. This is amazing, and this is really fun now. As an example, here's a Dockerfile where I'm building FFMPEG from scratch, and I'm also adding hardware acceleration. So this will use the GPU to decode and encode. So it'll speed up your processing a lot quicker if you're handling a lot of videos. And this is part of the Dockerfile that I used to build the project that I talked about earlier. And then your YAML manifest for Kubernetes, it's also pretty straightforward. This one in particular, I have some monitoring built directly into it. You can see I'm shipping things directly to a trace agent, which is Datadog in this case, enabling something called statsd, which allows you to see things like how many images am I processing per minute, logs, volumes, so I put all my downloaded videos in a mounted volume. And so when we get to having all these moving pieces, especially with something like Kubernetes, observability in your systems becomes a necessity. We can no longer keep the entire state of the architecture of our systems in our head, and it's more and more becoming a thing where no one person can maintain the entire state of our systems within their head at a time. So my favorite example of the instance where you'll need observability is pipelines. So this is from that project that I talked about before. And so I have a scraper API. Unfortunately, YouTube and Instagram gather up a lot of videos, but they don't make it easily scrapable. When Google was starting out, they were able to scrape the entire web and get that data set because everybody's open and you're able to get data from everywhere. That's not so much the case anymore. Instagram and YouTube don't make it easy to get videos. I'll just put it at that. And so you need to build a container that's running and runs a web browser, and then control it with JavaScript to scroll through the page to actually get a list of the videos. And so that's like the beginning of the entirety of the complexity. And so I use Beautiful Soup to extract URLs, download the videos according to their terms of service, run it through an Inference API to see if there are clocks and on which frames clocks occur. Using a model called YOLO, you only look once, and it will actually find a labeled set of things within video and where it is. And then finally, use FFMPEG to extract the snippets of those clocks. And so one of the tools for observability is distributed traces. So in that previous slide, we kind of saw, what is a unit of work in that system? Distributed traces allow you to see your units of work as they pass across all of your subsystems. So rather than just pressing a button, hitting a URL, starting that API to begin scraping, seeing nothing and wondering what's going wrong, you can start to see on which subsystem those errors are occurring. And so you build up and you have kind of this graph. And that graph shows you the entire path of the units of work through your subsystem. So here we can see, this is from another project where we have a sensors API and an Internet of Things front end. We can see the entire request as it passes downstream through all the services. We can do the same thing with metrics. So we can see bottlenecks in the CPU, disk space, memory usage. With your GPU, when you're training, you have a limited amount of memory. And you want to use up as much of that memory as possible so you're being super efficient on your cost if you're deploying to the cloud. And you can also use it to see how many frames per second you're tracking, generating, if there's actually any clocks, that sort of stuff. And the way that you add observability is via Daemon Sets. So Daemon Sets are containers that run once per node or once per computer within your cluster. And you can set it up. And here I've got one from NVIDIA that's exporting the memory usage, CPU usage, and also the power usage. And you generate a secret, ship it. There's 2 YAML files. And then you start to see graphs of what's going on. And so I mentioned before the hardware encoder usage. You can see if your code you've written is actually utilizing the encoder, how much memory you're using, so you can see how many concurrent instances of your service you can have running at a time to max out your GPU usage. And so with logs, you can see an auditable trail of side effects, so all of the things that are occurring within your systems. And you can see a history of each individual system component. And so here we can see this is when I have inference going, and I can see when I have clocks that happen within my videos, and I can check and see that everything is working fine. So object detection alone opens up completely new platforms. And with machine learning, we can start to think of images as being code itself. And so I just want to run through a few examples of the sorts of things you can do. So Binny is a self-sorting recycling bin. I don't know how many people here get confused when you go to a recycling bin about what is what sort of recycling and what is allowed and not allowed. I think the trickiest one is composting. You can never tell if it's been ruined or if it's still good for composting. This is a project I did, DAB and T-pose controlled lights. So this uses OpenPose, and it's that model that I showed earlier. And so I built up a data set of myself in my office, dabbing and T-posing, and then I trained on that data set to be able to do it. Yeah, kids love it. Yeah, and I actually deployed it to this new platform. I was talking before about edge stuff. Jetson Nano is really cool. It's basically a Raspberry Pi for $99 that does GPU acceleration. And that'll run and do inference on the code that I just showed. And it's pretty great. Thank you. And yeah, Datadog is hiring. And all the code for the example of Kubernetes is open source. And you can go check it out and start playing around with it too. So build a gaming PC. Thanks.
Thank you so much, Kirk. One more round of applause.